sections.
That's not right.
That's not quite right. Conic sections. So if you peek ahead, all right, peek ahead, there's circles, parabolas, ellipses, hyperbolas, and then some polar stuff in review. But circles, parabolas, ellipses, hyperbolas, those are sort of the traditional conic sections. I say traditional because there's some crazy ones that we won't really talk about. Circles, parabolas, ellipses, and hyperbolas. Circles today, it's the easiest one. But why they get their name, or how they get their name of conic sections, shh, you guys are excited for a Friday. These are the different shapes you can get when you slice a cone, and actually it's a double cone, so be careful. A double cone with a plane. So a double cone means what you think it might mean. A cone, one on top of the other. That's a double cone. If you slice it straight across, like with the plane is perpendicular to the axis of the cone, if you slice that, you get a circle. So that's a pretty easy one because that's an easy slice. There's the circle. If you think about the angle that we're slicing at, so we slice it straight across, we get a circle. If we tilt our plane just a little bit and slice it this way, there's a circle, but we get an ellipse. So we first sliced it straight across, that was a circle. Then we sliced it at a little bit of an angle, that was the ellipse. If we slice it at more of an angle, and actually to do this one, the angle has to be perfectly aligned with the opposite side of the cone. We get, well, this will slide off somehow. You know what shape that is? Parabola. And if we slice it like straight up and down, this one's tricky because we don't have a double cone. So it would hit this side of the cone, but it would also hit the other side of the cone. And this shape would be, especially if there's one here and there's one up here, that's the hyperbola. So that's how you slice the cone a bunch of different ways to get those shapes. Again, the weird shapes are a point, a line, and two lines. So I'll just let that alone and you see if you can figure out how to slice that cone such that you get a point or a line or two lines. The point's easy. How would you slice the double cone to get a point? Yeah, like slice it like right at the middle there where that intersection is just a point. We're not going to do the special cases. We'll stick with the kind of the main ones. All right, so a circle. Standard form of a circle. I think you saw this in Algebra 2. Does that look familiar?
Yes.
Okay. X minus h squared plus y minus k squared equals r squared. HK is the center, r is the radius. So let's breeze through some of these. In fact, maybe even breeze enough to just like pick on people here. Not on Friday. I'll do the first one because that'd be kind of cruel. So the center would be careful with the signs. The center would be 5, negative 8. And the radius would be 4. I mean, I would think you would want to get picked for this, right? Still no. No. Sorry, people are getting picked. So on number 2, Zainab, what's the center of that circle? Correct. And Jameson, the radius? It would be 2, because that number is r squared. So r would be 2. All right, example 3 is sort of the backwards problem. Write the equation of the circle with radius 8 and center 4, 9. So x minus 4. Here's my favorite way to miss this problem. Plus y minus 9 equals 64. You got to put the squares on there. It's a dumb way to lose a point on a test, but it happens. Number 4, write the equation of the circle with center 0, negative 4, and radius square root of 7. So you could put x squared if you really want to emphasize that the point is at 0. You could go x minus 0 squared plus y plus 4 squared equals, what's the other side? Just 7, because if I square root of 7, we get to 7. All right, number 5. Number 5 and 6 involve one of your favorite things, all the math classes. Not proofs, it's second to proofs. Find the center and radius of the circle, but it's not in the right form. So let's group the x stuff, leave a little space, and group the y stuff. And that 11 is like kind of in the way, so let's just move him to the other side. Not soap. Soap is for factoring perfect cubes.
Yeah.
Does anybody know what we're going to do to make this work?
Well, you just make them and you just like do your perfect square. So you do like x minus 3 squared and y plus 4 squared. Then you add the non-x and non-y terms and put them to the other side.
Okay. Yes, it's b over 2. Just b over 2 is the factor. The name for this method, I don't even want to tell you the name because you're going to get trauma just from hearing the name of this thing. Do you remember what we're doing? Complete the square. Complete the square. So half of negative 6 is negative 3. But I can't just write x minus 3 squared unless there was a plus 9 there. So I put a plus 9 on this side and a plus 9 on the other side. Half of 8 is 4. Square that, I get 16. So add 16 to both sides. By adding 16 and adding 9, we turned those into perfect squares. Now they will factor nicely, and now they look like a circle. And then on the other side, 20 plus 16 is 36. That was convenient. So my center is 3, negative 4, and my radius is 6. So half of the middle term, square it, and add it to both sides. So I'm going to press pause and let you do number 6. All stars. All right, sketch the graph of each circle. This is easy, fun stuff here.
No, it's not.
Sure it is. Let's take the time to write the center and the radius. That way, we're less likely to make a mistake. So 2, negative 3, and then 4 in each direction. And then please draw a circle. I took off on the test. I did take off a couple points, like 1 or 2 people per class when their pictures weren't quite good enough.
Were they like a Rebecca circle?
They were pretty bad.
Was I one of them?
They had to be pretty bad to lose points.
Mine at the top?
There we go.
Oh,
I'm about to.
What? You don't like that?
the top right is a little okay.
A little flat, but the rest of it's pretty good. 3/4 of a good circle. Let's see. Negative 3, 5, radius 5. Again, it's not a game of connected dots. You're drawing a circle. That circle's pretty good, I feel like. This one sometimes throws people off. Probably nobody in this class, though. What's the center of circle C going to be? 6, 0, of course.
Are we your smartest class?
You are the smartest third period I have this whole year. Mm-hmm. Without a doubt. You have a true statement that's also affirming.
No.
You are my smartest third period I have this whole year.
Not this stuff.
Okay, number 12. That looks a little bit weird. Let's square both sides and see what happens. That would get us to y squared equals 49 minus x squared. And then if I added the x over, I'd have x squared plus y squared equals 49. Well, x squared plus y squared equals 49. That's definitely a circle. But you know how this is going to be different from the circle? Let's think about moving this backwards. So I move the x squared over, I square root both sides, and if you look at B, you might see the hint here. When you put the square roots on, what are you supposed to do? Put the plus or minus on, and for this graph, the plus would make the top half, the minus would make the bottom half. So when we see this, this is the top half of the circle. So just the top half of the circle, because it's the plus half of the circle. So what's part B? The bottom half of a circle at the origin, radius 6. But just the bottom half of the circle. That's probably my best half circle yet. And then see which part of the circle is that? Top half, radius 5.
But you only want to do a perfect square root, right?
Would it work if that was not if like 25 wasn't a perfect square?
Yeah.
I mean, it would. It's just you'd have to know, like, if it was the square root of 20, your radius would be whatever, 4.5-ish. So it doesn't have to be a perfect square, but usually it is, so that you can graph it relatively easily. 13, backwards problem. Write the equation of the semicircle, centered at the origin, with radius 12. This graph is below the x-axis. So I look up at my examples. I mean, well, if I didn't have the examples, I'd start with x squared plus y squared equals 144. And that would be 144 minus x squared with the square root. But it would be negative because I want it to be below the x-axis. Yeah. So most people are going to jump straight to the answer. But if you hadn't seen one in a while, you might start with what you'd normally think of as a circle and kind of work your way there. 14, pretty similar, but we're going to be above. So square root of 121 minus x squared. piecewise function. Write an equation of f. How many pieces of f are there? There's 3. So f of x equals, there is a semicircle. I want to do the, divide it up first. So when x is from -9 to -3, it's a line. I'm going to finish making the neighborhoods first, and then from -3 to 3 is the semicircle, and then from 3 to 7, and it looks like we want to include 7 because now be careful to make it a function and to make it have only one y value at each x value. I'm careful with, I'm not including -3 on one of them, but I am including it on the other. And it wouldn't matter which one I included because it's the same point, they match up. Let's do the middle one first because that's the one I'm most familiar with. We're just doing those. So that's square root 9 minus x squared. Alright, that was the easy one. This line, let's see, what do we have for a slope here? -2/3. So -2/3 x. And then, what do you think? I need b. A couple ways to do this. To me, the easiest thing would be just sort of visualize what would be b if we had a b. That makes sense. If I extended it, what would the y-intercept be? -2, especially if I did a better job of extending it. So -2/3 x minus 2. And then same thing on the other side. Slope is 1. Oops, not y equals. We already have the y equals. X. Can you tell what that's going to be? Ish. I'm not sure about ish. I don't like that. Let's do this a better way. So slope is 1. Do you remember this format? Excuse me. Of a line where you do y minus y1 equals m times x minus x1? Point slope form? We love that form in calculus. That's the only form we use in calculus. Because we're allowed to leave it as the final answer. And so if you have a point and a slope, we like that form. So let's pick the point 3, 0. That would be an easy one to pick. Oops. Slope is 1 times x minus 3. So x minus 3. So we were right. It did intersect at -3. So there's our piecewise function. Part B, what is the area between the graph of f and the x-axis on the interval -9 to 7? Okay. Seems like a weird question, but speaking of piecewise, I think I'm going to go piece by piece here. That's a triangle, so 1/2 base is, careful, people will look at that and tell me the base is 9. No, the base is 6, and the height is 4. So there's that piece. That would be 12. Plus, that's half a circle, so 1/2 pi times 3 squared. So 9 pi over 2 for my circle, or my half a circle, I guess. And then my last triangle, another 1/2 base times height. 1/2, 4 times 4 is 8. And so if I add them all up, I get 20 plus 9 pi over 2. If that feels like a weird thing to do, it's because that is a calculus thing that we just did. We didn't call it calculus, so. What's not good? 2 triangles and a circle? Like, okay, it wasn't a calculus thing we did, it was a geometry thing we did. How about that? You'd rather do calculus than geometry?